Okay, so what we're now going to do is take a look at a different perspective for buffers, and that is called the buffer zone on a titration curve. So what we're going to do, we've got a lot of stuff going on in this unit, and it's real easy to lose track of. So what we're going to do now is we are going to look at a variety of different places on the titration curve and how to do that math and quick review of some things. So first of all, what is the pH of 100 milliliters of a 0.3 molar solution of our formic acid? Okay, so this guy here goes back to part 1, right? You don't even need the 100 milliliters. The 100 milliliters isn't even important in this because you have the concentration. It's a weak acid, you've got the Ka, so all you've got to do for this is do a traditional Ka problem. So your equation is going to be HCH2O plus water comes over here to H3O positive, and then CH2O negative over here. And you should know then that Ka is 1.8 times 10 to the negative fourth, and that's going to be equal to H3O positive times CH2O negative divided by HCH2O, like so. And I got an I, and I got a C, and I got an E, and I don't care about this. So this is a 0.3 and a 0 and a 0. And so this is going to be a minus x and a plus x and a plus x. And it's going to be 0.3x and x. And I can ignore this here, but not over here. Again, this is a part 1 kind of a problem. So you're going to end up with x squared over 0.3 is equal to 1.8 times 10 to the negative fourth. So 1.8 times 10 to the negative fourth times 0.3, square root that guy, and then negative log him. You end up with a pH of about 2.13 as your answer here. So that's about a 2.13. All right, that is a traditional part 1 kind of a problem. That's the stuff that Mr. Comerford taught you in part 1. All right. Now what we're going to do is we're going to take that 100 milliliters and we're going to titrate it with 100 milliliters of 0.3 molar sodium hydroxide until the equivalence point is reached. Okay, so this goes back to what we talked about in part 2 of my half of this unit, and now we're talking about equivalence points. So first of all, what we have to do is we have to recognize that we have 100 milliliters of 0.3 molar HCH O2, although I think, no, that's okay. And then I'm mixing that with 100 milliliters of sodium hydroxide, 0.3 molar sodium hydroxide, which is the OH that's there. And when I mix them together, remember they dilute each other, so it's really going to be 100 200ths and 100 200ths of this, which makes sense. So that's going to end up being 0.15 molar, and that's going to end up being 0.15 molar of everything. Now, if we examine this as presented, it becomes problematic, because as presented, this is HCHO2 plus OH negative comes over here to form water plus CHO2 negative. Water is on the products side. So what did we talk about doing before when we were at the equivalence point? We talked about taking it all the way over and then flipping it. So if I've got 0.15 and 0.15 and who cares and 0, I'm going to take this all the way over so that I'm left with none and 0.15, and now flip-flopping it around. And why can I flip-flop it around? Because if I flip this guy around and look at it from the opposite perspective, then I'm looking at CHO2 negative plus water comes over here to form OH negative and HCHO2. And the reason I like that is water is now on the left-hand side, and we're talking about Kb, except they didn't give us Kb. They gave us Ka, except that if we know Ka, we know Kb. So remember that Kb is going to be 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 4th. So that's going to be a 556 times 10 to the negative 11th over here. So that's 10 to the negative 11th. And I've got a 0.15 and a 0 and a 0 and a minus x plus x plus x and a 0.15 minus x, x, and x, except that I can get rid of this because it is unimportant, and so I end up with x squared over 0.15 is equal to 556 times 10 to the negative 11th. So 0.15 times 556 times 10 to the negative 11th, and then I square root that, and I end up with x being 2.89. Oop, I must have done something wrong there. 5.56 times 10 to the negative 11th times 0.15, and then square root that. That's 2.89 times 10 to the negative 6th. And remember that x is the OH negative, so then the pOH of this is a 554, which makes the pH of this an 846. So again, all of that is old news. There's nothing about either of these problems that has anything to do with buffers yet. And all of this is old business. So this is a quiz 1 kind of a problem, and this is the first part of part 2 problem that's going on there. So this covers us at the start, and this covers us at the equivalence point. So if I were to erase all this so that I had a place to write on my graph here, and I were to draw this guy out, I was starting at a 213. So my starting pH is down here at about a 2.1. That's before any titration occurs at all. And then if I were to titrate it, I'm going to go up and up and up and up and over. And I apparently just calculated that my equivalence point here, if I went over there, was at about an 8.46. So we'll call it 8.5. So this is a part 1 kind of a problem. This is an early part 2 kind of a problem. Okay? All that is old news. What I'd like to talk about now is I'd like to talk about what happens in between here and here. Because there are some great things that happen between those two spots that make it very easy for us to do some calculations once we realize what is actually occurring there. So it's going to turn out that this is going to be called the buffer zone. And let me explain why and how it's the buffer zone and what we can get from it and how we can make our lives easier there. So let's do the same problem that we did before, but let's see what happens when we only go halfway. That we only go when only 50 milliliters of the 0.3 molar has been added. So again, this guy here was at like 100 milliliters. What I want to do now is I want to go to 50 milliliters. I only want to go halfway. So basically, it is 100 milliliters of 0.3 molar HCHO2 and then 50 milliliters of my hydroxide, which again is also 0.3 molarity that's there. All right. So what do I do when I mixify these? Well, that's going to be 100 and 150ths of 0.3, so that's going to be 0.2 molarity. And that's going to be 50 150ths of 0.3, and that's going to be 0.1 molarity. So if I take my HCHO2 plus my hydroxide, and that's going to come over here to make water, CHO2 negative, and I got an I, I got a C, and I got an E. Right off the bat, again, I know that this is not where I want to be because water's on the right-hand side, but I can deal with it. So this is 0.2, and this is 0.1, and that's nothing. And I know that because water is over here on the right-hand side, I want to take this all the way over that I possibly can, except that in this case, it's not at the equivalence point. At this case, I can only go as far as this will allow me because he's my limiting reagent. I'm going to run out of him. So I'm going to lose 0.1, and I'm going to lose 0.1, and I'm going to gain 0.1 over here, and I'm going to be left with 0.1, none, and 0.1 over here. Now let's stop. Check it out. What have I got? I have got 0.1 molarity of that guy who is a weak acid. And I have got 0.1 molarity of that guy, who is his conjugate base. Well, what does that sound an awful lot like? That sounds an awful lot to me like a buffer, because what I've really made here is I have made it so that I have some weak acid and some weak base that are present. I have made myself a buffer in there. So if I were to simply go ahead and plug these guys into my Henderson Hasselbach equation, check out what would happen. I would get pH is going to be equal to, again, the pKa plus the log of my base to my acid, or my pH is going to be equal to the negative log of 1.8 times 10 to the negative, oh, what was that number? Fourth, plus the log of 0.1 over 0.1, which is going to drop out. Oh my gosh, look there. The pH is simply equal to the pKa, or in other words, it's the negative log of the Ka, 1.8 times 10 to the negative fourth. And so my pH is simply going to be 3.74 that's there. So what we have just identified is a very, very important point. And that very, very important point in our graph that's here, the halfway point, is called the midpoint. The midpoint. And the midpoint on a graph is a very special point. It is halfway, this point here is halfway to the equivalence point here. So let's say that this is 100 milliliters, then your midpoint is going to occur at 50 milliliters. If this here is at 38 milliliters, then that would be at 19 milliliters. And you get the idea. If this here is at 12.6 milliliters, then your midpoint would be at 6.3 milliliters. And what's so special about the midpoint is that at the midpoint, what you have is you have the HA that equals the A negative in a buffer. And so at that point, if you were to simply go over and figure out what the pH is at that point, the midpoint, that would be the Ka value, technically the pKa value. So all you got to do is find out where the midpoint is, and all of a sudden you know what the K value is for the substance. So take a look at this. This is a very typical problem. This problem says, what's the Ka of this unknown acid? So it's pretty obvious that my equivalence point is here, and it occurs at 10 milliliters. So that's my equivalence point. So if my equivalence point is at 10, that means my midpoint is at 5. So that's the midpoint, that's halfway. So what I'm going to do is I'm going to go over until I hit the line, like so. And then I'm going to draw a straight line over from there. And that looks to be at around right at 3.5 or so. So that means that the pKa of this acid is 3.5, or the Ka of this acid is 1 times 10 to the negative 3.5, or has a value of 3.16 times 10 to the negative fourth, which is the same thing as 1 times 10 to the negative 3.5, if you were to put that into your calculator. So the cool thing about this is if you know what the equivalence point is, then you know what the midpoint is, and if you know what the midpoint is, you know what the K value is of your acid. So you can use that to identify that acid at the appropriate time. Now, one last thing about this then, what's so important is that if this is the buffer region, and if this region right here is the halfway where the acid and the base are equal to each other, then we can make some obvious judgment calls about what's happening here versus what's happening here. So check it out. If this spot here is where the acid and the base are equal to each other, see that there? They are equal to each other. then what's happening here in this section here? Well, it's slightly more acidic, right? And if it's slightly more acidic, then that must mean we have a little bit more of our weak acid than we do of our conjugate base. So in this spot right here, the acid is greater than the base. At this spot right here, the acid is equal to the base. And then at any spot over here, my acid is going to be less than my base. The weak acid is going to be less than the conjugate base as far as the buffer is concerned. So if we were to use this idea in our Henderson Hasselbach equation that is here, that spot there is where that and that are equal to each other. This spot here is where that is big and that is small. And then this spot here on the graph right here is going to be where that is a little bit bigger and that is a little bit smaller here, but they're all going to be buffered in that zone. Now, back in the day, they would make you calculate what the pH was going to be at any one of these given points, but nowadays they won't. The only thing that they might make you do is this midpoint, and the midpoint is ridiculously simple. All right, so let's check this guy out here. It says the above graph is a titration curve showing the titration curve of hydrozoic acid. On the above graph, show where each of these circumstances would occur. So part A, where would the amount of weak acid and weak base be the same? Well, let's see. I'm going to call my equivalence point here at about 0.6 liters. So if my equivalence point there is at 0.6 liters, then 0.3 liters is around here. That's my midpoint. That's 0.3 liters. And so that's my midpoint that's right there. That's the equivalence point. And that's the midpoint. That would be part A on this. That's the midpoint. Where is it that my acid is slightly more than my base over here? Because again, that's my acid and that's my base. Well, that would be any point along this part of the graph. That would be part B. Any part between here and here would be that guy there. Where would it be nearly 100% of the conjugate base? Well, nearly 100% of the conjugate base is going to occur here, part C. That's the equivalence point. Because remember, at the equivalence point, what you've got is you've got HN3 plus OH negative comes over here to form H2O plus N3 negative. And at the equivalence point is where it's gone entirely over 100% of the way over here. And so the equivalence point is part C. Where is it that I have nearly 100% of my weak acid? Well, that would be my starting point. That would be part D here, because that's where I have my weak acid and I haven't done anything to it yet. And then part E says, where is it that my acid is less than my base? Well, that would be any part along this portion of the graph right here. So this guy here is going to be my acid. This guy here, my acid is going to be more than my base. At this point here, my acid is going to be equal to my base. At this point here, my acid is going to be less than my base. And at this point here, I have just about nothing but base. It's all about that base. All right. Number 2 says, what's the approximate Ka of hydrozoic acid? That's easy. All I've got to do for that is find the midpoint. So we said that the midpoint is around 0.3, which is around there. So that's the midpoint. Now what do? I take that and I go over to about right there. So I don't know, what are we going to call that? About 4.5? We're going to call that maybe about 4.5. So that's my pKa. So this guy here, my pKa is 4.5. So that means that my Ka is 10 to the negative 4.5, or 4.5 negative 10 to the is about a 3.2 times 10 to the negative 5th, give or take a little. And then finally, our last one is what was the original concentration of the hydrozoic acid. So this is an equivalence point kind of a problem. So this guy here, I know that that point there is 0.6 liters. And what do I know at that point? I know that my moles of my acid and my moles of my base are the same. And so what I get here is I get MAVA equals MBVB. So the molarity of the acid is what I want. It took 0.30 liters according to this problem. And then I titrated it with 0.2 molarity of my strong base. And the equivalence point was at 0.6 liters. And so, consequently, this is 0.2 times 0.6 divided by 0.3 gets me a 0.4. So the molarity of my acid is about a 0.4 molar solution of hydrozoic acid.